Good evening to everybody. My name is Fabio Gianaroli. I am PhD student of Professor Vitetta and Pancaldi. In the last year, my research activities focus on the analysis of time-varying behavior of PowerLine communication channels. The main goal of my research activities was the modeling of PowerLine communication channel as linear periodically time-varying systems. In this slide, I will show the physical phenomena at the base of time-varying behavior of PowerLine communication channels. I will present a possible mathematical model to describe a linear periodically time-varying channel, and I will show a PowerLine channel sounding developed to acquire the channel response of PowerLine communication channels and some experimental results acquired in our lab. The transfer function, so as the impulse response of PowerLine communication channels, depends on two distinct aspects. On one end, it depends on the topology of the network, and this is a time invariant characteristic of the system. On the other hand, it depends on the set of home appliances connected to the PowerLine networks. The set of home appliances connected to the PowerLine network changes during the day, and this is a long-term variation of the channel that is not periodic. But in the most of cases, the input impedance of home appliances shows also a short time variation that is synchronized with the mains. This can be justified because the mains excite the nonlinearities of power supplier circuits of home appliances. Experimental measurements showed that PowerLine communication channel can be modeled as a linear periodically time-varying system with a period of 10 milliseconds. In many fields of science, the most common way to describe a time-varying system is based on the impulsive response. In a linear time-invariant system, the impulsive response doesn't depend on the time, but for a time-varying system, it depends on the time, and in particular, in the case of a linear periodically time-varying system, it depends on the time in a periodic way. In my model, the period of the system is n0, and so for a linear periodically time-varying system, the impulsive response can be expanded in series of Fourier. This is the series of Fourier, and these are the DFT coefficients. By introducing this expression in the input-output relation, we can obtain a new expression that is called the ZD series. The ZD series expresses the output of a linear periodically time-varying system with period n0 as the sum of the output of n0 filters, where each filter is where the output of each filter is multiplied by a complex exponential. By truncating the order of the model and the length of the impulsive response of each filter and exploiting the Hermitian symmetry of DFT coefficients, a new model can be obtained. This is the model used by me to fit the PowerLine communication channel, and all parameters of this model are real. This is a graphical representation of my model. The complex exponential are replaced by cosinusoid and sinusoid, and the previous filter with complex impulsive response are replaced with filter with real impulsive response. To identify the parameters of my model, I have developed a channel sounder tool. This is a block diagram of my channel sounder. It includes a personal computer to configure the operation of the channel sounder and to transfer the data, a statics-free FPGA development board that is the core of my system, a data conversion interface with two analog to digital converter, a two digital to analog converter, and the last block is a power analog front end to connect the data conversion interface with the PowerLine communication channel. The channel sounder transmits a probing signal on the PowerLine communication channel and acquire the channel response. By post-processing, the parameters of my model can be estimated. During the development of my channel sounder, I have addressed the two main problems. One is the memory resources required by my channel sounder. My channel sounder operates with a sampling frequency of 100 megahertz and can acquire a channel response with a length up to 5 seconds. And so there is a problem because in a typical channel sounder for a linear time invariant system, the length of acquired channel response depends only on the frequency resolution required by the user. But in the case of a linear periodically time varying system, the length of acquired channel response depends also on the length of the period. In my case, with a sampling frequency of 100 megahertz, the length of period is 1 million of samples. So for each period of operation, my channel sounder requires 2 megabytes of memory for storing the probing sequence and 2 megabytes of memory to store the acquired channel response. So the channel sounder, to correctly operate, would require a data connection to the personal computer with a bit rate of 3.6 gigabit per second. To overcome this problem, I have adopted a store and forward approach by exploiting the DDR2 memories available on the FPGA development board. The channel sounder, before each channel sounding operation, load the probing sequence on a DDR2 memory, and during the channel sounding operation, the channel sounder saves the acquired data on another DDR2 memory. And only at the end of the channel sounding operation, the channel sounder transfers the data from the FPGA development board to the personal computer. The other problem is related to the design of power analog front end for the bad properties of PowerLine communication channel. For instance, the presence of power signal at low frequency, the low input impedance of the channel, and the presence of strong impulsive noise. This is a block diagram of the project developed on the FPGA. It can be divided in 3 main modules: the control unit, designed around a virtual microprocessor NIOS 2, and 2 real-time modules to manage the probing sequence and to manage the channel response. These 2 last modules operate with a maximum clock frequency of 300 megahertz. In these last slides, I have reported a photo of my experimental setup with the personal computer, the FPGA development board, the data conversion interface, and the power analog front end. This is an example of time-varying transfer function acquired in our lab along 2 periods. And these are the impulsive response of a model of order 2 fitted on the channel under test. This is the list of my publications. Thank you for the attention.
Oh, thanks for your presentation. Questions? Okay, thanks again. The next one is, the next candidate is Matteo Interlandi.